Okay. Thank you very much, Marta. I'm sorry for not to come next week in Estonia. I'm sorry I have an intervention in my mouth and it's not possible. But I'm sorry too. I'm going to start changing the topic a little bit. I'm going to speak about methods for obtaining, identifying, and interpreting microvertebrate remains in quaternary sites. The most important questions about that is what are the small mammals, which are the main groups, how we recorded them in archaeological sites, and how they arrived to these archaeopaleontological sites and why we study these little things. What are small mammals? Normally, a small mammal is a thing as small than a rabbit, but it's not really true because there are, for example, uh, small kitties or small monkeys or cats that are not small mammals. However, beavers or capybara that are large rodents are included inside the small mammals because are rodents. And we consider also small mammals, moles, bats, hedgehogs, and voles and dormouses, for example. This is a little bit a scheme of the phylogeny of Eutherian mammals. And you can see here the evolution of the different Eutherian mammals. And we can see here the separation of the main orders of small mammals that we can find in an archaeological site. For example, Chiroptera are bats, Euliplotifla are mainly the European or insectivores, to include shrews, hedgehogs, and moles. And after we have rodents that include the various families, etc. And this is only here the general morphology of a mammal tooth. Okay, we can found here actually in nowadays that the rodents, for example, represents 42% of the species in the world, and bats the 20%. There is a lot of species of bats and rodents, and also in the quaternary we can find a large diversity of these species and taxa. Why are important? Because they have for the small size of this kind of animals, they evolve quickly because they are very sensitive to climate changes, to environmental changes, and it's important to see in some cases for biochronological reconstructions because we have a lot of different species during the quaternary that change and evolve, and if we have the association, we can know more or less the chronology of the sites. And after, because this rate of rapid evolution, of quick evolution, we can also can see the changes in environment when we have determined small mammals or small vertebrate assemblage in one or other sites or various sites. It is only here. Okay. This is a little quick video of the process of the water screening sediments from Atapuerca for recovering the small vertebrates from this site, only for fun. Which are the main groups in the species? I advance this thing a little bit. The main groups, there are others, but the main groups that we can find in European sites are the order Olipotifla insectivores, with three main families and subfamilies. After bats, Chiroptera, where you can find these two main families. And other Rodentia, you can find these three main families and subfamilies that are the material that you can find in archaeological sites from early Pleistocene to early Holocene in Europe, more or less. The insectivore. What is an insectivore? Insectivore, as the definition said, is a small mammal with is a mammal with a small size that is plantigrade with the fingers like that. I don't know how to describe it for in the computer. And the main thing is there are feet insects, and here more or less is like a rodent, but with the mouth and the nose in is acutate. Here a mole and a hedgehog that are all insectivores. The insectivores appears more or less 102 million years ago, before extinction of the dinosaurs. But after the Kati limit, 65 million years ago, that is here the end of the dinosaurs, there are a dispersion of the of orders and super orders of these small mammals. And in the Eocene, more or less 55 million years ago, appears the current subfamilies of this kind of small mammals, mainly Talpinae, Rhinacidae, Soricinae, Desmaninae, and Crocidurinae. Here, a little bit to see the dentition of these small mammals. I have also some videos for fun only. With the morphology of an insectivore, in this case is an Erinaceus. You can see here the cranium with the teeth. The characteristic of these small mammals that they have the teeth in form of W. You can see here. This is called the lambodont. And also, there are here the lower molars, and these are upper molars. You can see here more or less. It's run automatically. Okay, you can see here the upper molars. Here is a mandible, also from an Erinaceus, and here the dentition with the lower molars here, also in form of W. And for example, I put these images because mandibles and cranium and teeth normally in this kind of mammals, in the small mammals, are diagnostic for identify the species. But also there are in other insectivores like moles. You can see here an arm of a mole that other kind of bones are also diagnostic for the identification of the species. They have the arms adapted to burrow, and the bones very characteristic. Is this green, for example, is the radius. This is the humerus, ulna, and also carpals and phalanges are very characteristic from talpa. Are different from other small mammals. Okay. Uh, we are going on with chiropters. Chiropters are mainly bats. Are these bats these mammals that can fly, and they have the wings. We call the bones are also large. And also, for example, in Europe, there are bats that eat fruits that are frugivores, and also there are bats that are insectivores like the other small or mammals. In the case in Europe, for example, all bats that we can found are insectivores, and after there are other kind of bats that sucks blood from cows. You know, normally are little chiropters that sucks blood. Phylogeny and evolution of bats. The first really bat with flight and echolocation and all the things that bats are nowadays appears more or less 5 to 52.5 millions ago during the Eocene. Here we can find the phylogeny that they're very complex than the insectivores with all these families really and other and superfamilies and etc. And also the different genus that we can find from the ancient fossils to nowadays. This is the morphology of the cranium, mandibles, and teeth of bats are similar in morphology, in shape with insectivores because are insectivores too. Are the morphology of the teeth are also made in W, that it's called the Lambodon morphology of teeth. You can see here a cranium, but after, if you remember the slides before, are very kind of different the morphology. If you can found a mandible or cranium, they have this caninum very broad. This is the canine with the mandible, and this is another mandible, and you can see here if it moves. Also the morphology of teeth, and this is the accent ramus of the mandible, etc. Okay. We are going to pass. Also, bats for the adaptation to flight could be recognized with other bones like humerus. This is the different. This is the epiphysis, distal epiphysis of the humerus of bats, and you can see here at the morphology of the distal epiphysis is different in the different species. Here, a lot of species that we can find are all these species are nowadays species, but you can find some of them in archaeological or paleontological record during the Quaternary. And the more common species that you can find normally are this one, Rhinolophus perunecinum, and Miniopterus, and this one that is a Myotis. Rodents. Here I have another video from a castor. The rodents are the most abundant mammals in the world, and also I think maybe in Quaternary are the most diversified species. Also, you can find in archaeological and paleontological sites a lot of species if you have enough material to recognize the taxa. And this is the definition. They have two incisors to snow. The incisors are normally in all rodent species have a continuous growth. After in other species, also molars have this kind of things. The first rodents appears 58 million years ago, and across Eurasia and Africa in the Eocene, in the Eocene 22 million years ago. Here, more or less, the different orders that evolves from the ancient forms of glidids, Uroconodglides, and also you can see that here you can find that lagomorphs or rabbits and rodents are common ancestors. Okay, this is the morphology of the cranium and mandibles of rodents. You can see that are different from insectivores and bats. The main characteristic of a cranium of a mandible, rodents and also lagomorphs, rabbits and picas and the other, and lepus, for example, they have incisors here. After stop, after the incisor, they don't have any other teeth, and after they have three molars. The smallest, the smaller species have three molars. Other bigger species are one premolar, maybe P3, and the others have also P3, P4. But normally, the smallest species that you can find, like mouse, like a mouse, a mole, a mole, no, sorry, a bowl. They don't have any premolar, any premolar and caninum. They have only incisors, and after they have three molars. And here, the morphology of the caninum is the same with the two pronounced incisors, and after molars. And the morphology of teeth, it's more variable in the different families that we can see now, more or less. This is the mandible. Okay, this is the three, more or less, big families that you can find in archaeological sites. This is arbicolins, are bowls. They are very famous species of this kind of vertebrates. These are first lower molars with this morphology, triangular morphology, are very typical of this species. This is, for example, a water bowl. These are one of the most abundant species in Quaternary. You can find a lot of different things of arbicolins. After we have mice, this is a rodent, typical mice, with upper dentition and a lower dentition. And after, the other group that we can find in a lot of sites is with a lot of material are glirids, dormouses. This is then upper than no lower dentition from this kind of dormouse, and also this lower dentition. And you can see that there are difference in shape. And this is morphology of triangles of the teeth. Here you can find that, for example, mice are bunodont like humans, or are the morphology of teeth is bunodont with tubercles, different tubercles of teeth. This is one. This is M1, and this is M2, is lower. This is upper M1, M2, M3. And for example, the dormouses are an exception of these small mammals that have P4. This is a P4, M1, M2, M3. And if you can see here, they have the teeth in form of lophus, that there are these kind of crests that unify the cusps laterally, and this is like elephants, the same morphology that elephants have. The teeth is lophodont. Okay, here you go. More or less how we recover them, basically basic techniques. You can see before the water sieving with different mesh screens. We recover the sediments from the sites. We write all the signatures that the excavators make in the sediments, for to order not lose the things. After we put the sediment with a mesh screens with different size to wash the sediments. After when the sediment is dry, you can do nothing. You can pick up the sediments to separate little rocks from material. And after we have the small pieces that we can identify with a microscope and make pictures and make some quantifications like number of remains, identify a number of remains or minimum number of individuals, etc. Is an example of a big site from Atapuerca with the different kind of people working with different kind of, mm, of meshes here that is in this scheme more or less. This is a picture from Orce with another technique, but it's the same thing. Finally, with three different side meshes. Okay, sorting and preparation for the analysis. After we separate the little, in the case of the small mammals, mainly teeth or mandibles or cranium. After for the identification, we use reference collections and we make some measures to see if there are the one species or other species or different. And after for publications, for example, we make pictures from the microscope, electronic microscope, to see whether the characters that are from one or the other species. For example, here's a teeth from a geese, from a dormouse, and the two teeth from a podemus is a mouse. And here the references collections. Here this is the reference collection of the University of Ferrara. How they arrive to archaeological and paleontological sites. Okay, the main the main thing because you can find in an archaeological site mainly in caves or rock shelters. An accumulation of small mammals is because it's accumulated by predators. Normally, the owls or the nocturnal raptors or nocturnal birds of prey, diurnal birds of prey, and small mammal carnivores. After there are other things that we can accumulate these signs in a cave. We have this scheme that how the material is accumulated here and after the sediments are deposited above and they are disgregate and accumulate all these small mammals or small vertebrates. After okay. After there are other reasons, for example, natural death is maybe another reason because sometimes we can find in some sites the anatomically an species or fragments in connection. And if you can find, if you find a small mammal, I don't know, a bowl, for example, in connection in an archaeological site or in a site or inside a cave, it's for natural death, for example. It's easy to see. And normally when you find only fragments or something like this is for accumulation for predators. It's a different kind of predators that accumulate small mammals in caves or small vertebrates in cave, like all these diurnal, nocturnal raptors. What they do, they take the prey and eat uh, all the prey, and after they vomit the hair and the other parts that like bones that they don't can is not possible for do the digestion for them with all these things. And you can find here this thing that is called pellet. There are pellets from a bird of prey. And inside the pellets that are mainly hair and bones, you can find these small bones. This is a clean pellet with the different kind of, this is a mandible, cranium of an insectivore, rodents. This is also a zoo, I think, or postcranial things. And this is the process of formation of a pellet. You can see here the video with this ASIO. I think that this is ASIO Otus or something like this, that are going to repositate a pellet, and here to go. It's also for fun, and all the process is you can see here the process with the prey, after the prey inside the stomach, and after the process of the dissolved all the parts that they can dissolve that are not hair and bones that after regurgitate. Okay. Uh, for in the study of taphonomy, that is the the discipline that is dedicated to know how these small mammals arrive to an archaeological or paleontological sites. They divided in relation to the kind of predator, different categories in relation to digestion. When you will find digestion in bones, in digestion, in skeletal representation, breakage, and breakage of the small mammal materials. You can see here different kind of things, mainly different kinds of digestion. Also here we can find this is a red tooth shrew with different kind of digestion, moderate, heavy, and extreme, and it depends on the percentages of the kind of the digestion you have in your assemblage. You can put the assemblage in one category or another one. It depends on this kind of digestion. This is, for example, molars of arbicoline molars with light, moderate, heavy, and extreme digestion. This is the occlusal surface, and this is the lateral view of teeth. This is lateral view of the mandible of a shrew. And after also within incisors of rodents incisors. There's an upper incisor and lower incisor with different kind of digestion, light, moderate, heavy, and extreme. And after other things that can alterate or can modify these small bones, like large mammal bones, are water, for example, water abrasion like this, or roots that make these things in tooth, or the oxide of manganese, for example. Why study them? As I said before, the small mammals, mainly I study small mammals or small vertebrates, are important because they evolve quickly in the Quaternary and are important for chronological reconstructions, paleoecology, and paleoenvironment, and to see biological evolutionary history and evolutionary models. I'm going to pass this one. I focus in biochronology and paleoecology and paleoenvironment. That is the main focus for archaeology, I think. The biochronology, or chronology done with living or death, in this case, organism, is a part of the paleontology that they study when paleontological entities live their temporal ordering. This means that if you have a determinate a determined species in a chronological range, that maybe you can know that only exists in this range. If you can find association, a similar assemblage or similar association, you can know more or less that you are in the same range chronology. This is an example of trilobites from Sierra Morena, from Granada. That is another thing. Is not are not mammals, but It's the same thing. It's the same idea. You can do that with small mammals or with other entities. Here only the chronological chart of Quaternary to know that we are in a very small time period from 2.58 million years to present, but we can make the biochronology of ancient sites in with the small mammal assemblages. Also, if we have also other things to make that in, but it's interesting always compare and make a multi-proxy analysis in sites with all the things that you can study to interpret, to make the interpretations of the sites. In the case of Quaternary, Arbicolina rodents, these kind of the voles and lemmings are the most interesting family to use for chronological interpretation of the sites because they evolve very quickly, and we have a lot of species from the early Pleistocene to Holocene. This is only an example of the common of the most common species that are nowadays, like common bowl, water bowl, Norway lemming, or rat. The origin and phylogeny of these arbicoids, they come from chrysetids. Chrysetids are hamsters. This is a tooth of hamster that they have these cusps. This cusp in one point in the evolution, we don't know when, but the first arbicoids appears in North America 5 million years ago, and in Europe in 5.5. This is the American species that are the oldest known as Arbicolina species, and the oldest known in Europe is this one. And from these cusps appears these triangles, and probably the arbicoins evolved from a form of Quisnetita hamster, fossil hamster. This is an example of a quick evolution of Arbicola, is the water bowl, basically, in general. We have a lot of species here appears at the end of the Pliocene. 3.5 appears this species that evolves to another ones here that is separated here for the other species, and appears other here, and the convergence here and here, and we have all these species nowadays. This is done in 3.5 million years, and after this is the other genus of bowls that are separated between all these things. It's only an example to see that there are a lot of species that evolve quickly, and they are important to make a chronological range in some archaeological or paleontological sites. Sorry, I'm going to make some examples because it's very like this. We make this work in 2015 about the chronology of Pirro North. Pirro North is the site that is near to Apicena in the western part of Gargano. You can see here the quarry. The site is here. Appears lithic tools. This is the location, and this is the wet skin of sediments. In Pirro, we study in 2013, some years ago, the material, and we identified, for example, the arbicolinae are all these species, Anophagemys that are morphological variability of this kind of species. This is a picture of the photo. This is me in the University of Ferrara, and we identified 53 identified teeth and 26 individuals from this species. After we compare These specimens from Alophagiumys rufoi with other specimens from Sierra Atapuerca, the lower layers from Sima elefante, Alophagiumys labocati, and the lower layers of Grandolina with Alophagiumys chalinae, is another species of vole. All these ones are extinct voles. And we compare these things. We can see here, for example, with the index. What is an index from weight to length. This is not exactly this one, but more or less. That, for example, the Labocati appears here, and Ophidium chalinae appears here, and the Rufoi appears here, and also here and here. And you have the other species here. All these things, this is a manuscript with more things, but mainly the we can say in this moment that Pyronos 13 have the age between 1.4 1.6 that are inside in the Alophagiumys zone, and that is older than the older sites in the Iberian Peninsula, for example, T7, 14, and Barranco León. That we appears here, they are human remains. For paleoecology and paleoenvironment, we have more or less here a scheme of the different kind of rodents, for example, that are directly connected with a kind with a type of habitat. For example, the hamster is an open meadows. Other genus of Microtus maybe are more or less open, and other are, for example, aquatic, or these ones that are the dormouses are more related with forest. Well, with that, we can reconstruct with a small mammal association the past environments of the archaeological site that we study. For example, this is the current environment in Sierra de Atapuerca. This is the reconstruction 1 million years ago, and the remains of Homo antecessor. And for example, this is the current landscape in Asturias, in northern Spain, where there are a lot of Neanderthal remains at El Sidrón. And this is the reconstruction of the landscape in the late Pleistocene, when the humans are accumulated. Only here a scheme of the climatic fluctuations during the Quaternary. We have the marine isotopic stages. That pairs are called periods that you can see here. For example, MIS2, MIS6, MIS8, 10, 12, and others. And the odd numbers are one periods, 11, 9, 7, 5, for example, or the current one that is marine isotopic stage 1. We use different kind of methods, distributing the small mammals assemblage in different kind of habitats to reconstruct the environment and the landscape. This is only an example of a publication and the different kind of landscapes that you can find to distribute these small mammal assemblages. Also, we use other methods for reconstruct the climate, also with the partition of the small mammal assemblages in different kind of climates in this case, with a different formula to calculate mean annual temperatures, warmest month or coldest month, or mean annual precipitations. Also, other methods to reconstruct the climate and the temperatures and precipitations. That is the intersection of various species. You have these two species is an example with two current species. You make the intersection, you take points of coincidence of the two species, and these points you can extrapolate to 30 years maps of precipitations and temperatures, and you can extrapolate the temperatures and precipitations of sites that you are studying. I'm going to put an example about the environmental and reconstruction. This is a Neanderthal and modern human context. This is a manuscript that we published also in 2015 from Fumane Cave. Fumane is here in Monte Lessini, about 350 meters. We can see here in northeastern Italian peninsula. We have a very large stratigraphy with different macro units, R2D, and with Neanderthals anatomical modern humans occupations. You can see here the scale, and these ones are the occupations, all these layers that you can see here in a stratigraphy, also the lower parts. Sorry. We had the radiocarbon dates also with the different ranges from 44 sorry 44 to 35 kilo years, and also the calibration of that thing with these two curve of oxygen to see more or less the evolution from the lower layers to the upper layers chronology. In this case, for example, we have a clear chronological dating. It's not necessary make the biochronology with small mammals. Also because more recent in time, the small mammal assemblages are very similar to nowadays and it's more difficult to make interpretations about extirpation or extinction of a different species and make the chronological interpretations. Okay, this is the largest assemblage that we found is very, very rich in Fumane with 8,657 identified specimens and more than 4,000 individuals, 29 taxa, and more or less we have all these things that are there here, different kind of teeth, and these are rodents. Mandibles of insectivores that are here. All these ones are insectivores, and no, sorry, are bats, and here the insectivores. And the more characteristic species maybe are Chionomis, Hicetus, and Microtus. They are two bowl species. This is another bowl species and a hamster that are not currently represented in the Italian peninsula, and are indicatives or so for some things. For example, Microtus is a species that currently inhabits in North Europe and is indicative of relative cold climatic conditions or cold and humid climatic conditions. This is the figure with the sequence, the calculation of landscape, temperatures and precipitations, and the diversity of small mammals. And we can see here, for example, the evolution of landscape, the evolution of temperatures, and there are fluctuations. I put here in red the warm periods and in blue the cold. And you can see here that these are Musterian levels with theoretical Neanderthal occupations and Origin levels with modern human occupations, and you can see that they are well adapted to their environment because they lived in warm and cold periods indifferently. Also, Neanderthals and anatomic modern humans are the same thing. As to explain the two things combined, biochronology and paleoenvironment, now we are working in the lower layers of Sima elefante in T7. This last summer we found a face of a human face that is is now under study to publish. Sima elefante is that site in Sierra de la Puerca. I think that Carlos speak about that before. It's only the Sierra de la Puerca plan structure with the trenchway. Here, the first site that you find when enter to the trenchway railways Sima elefante. And this is a picture of the excavation, the stratigraphy. This is stratigraphy is complicated. And after the lithostratigraphy, where you can find that, for example, the upper layers are Middle Pleistocene in age, the 18 and 19. After there are these layers that are mainly more or less sterile. And from TE14 to T7, there are a lot of small mammals that we can found in 2007, I think. A human mandible with lytic tools here in T9, and this year we found a human face in T7. Okay, these are the main rodent species that we found in T7. In really are the same species that appears in T9. T7 are probably Calabrian in age, early Pleistocene, with the same age or more similar age to T9, 1.2, 1.4. We can find the typical species from similar elephante like Arbicola jacobea, this one, Alophaiomis labocati, nutiensis, and other species that are different kind of bowls. There are two different kind of mice, and this is a dormouse that are typically from these chronologies. Here, the table of representation, where the stratigraphy, the upper part that is Middle Pleistocene, and the lower part that is early Pleistocene in age, with an age more or less of 1.4, 1.2. The most interesting thing that is we compare the rodent assemblage from the T9 to T7, and the association is more or less the same, but the percentage of representation of species are different. In T7, we can see an open forest landscape with water coasters, with the most abundant species are, for example, this one, Arbicola jacobea, represents 10%, or Alophaiomis nutensis, together with Castillomys rivas, represents 28 and 32. And the representation here is very different. We can found here layer remains from other species that indicates that maybe forestry component of T7 are very more important than in the T9, that the landscape was probably more open than nowadays. And here the most characteristic species that indicates that things is Alophaiomis nutensis, Arbicola jacobea, this is Apodemus sp, and we have here Castillomys rivas. And to finish, more or less, I'm going to speak about the new techniques and improvements that are, are are developed or has been developing in these last years with the study of small mammals. For example, years ago, 2 or 3 years ago, is that developing the methods of the reconstruction of climate with the 18 oxygen, with the composition of tooth from bottom and lower incisors. Here, for example, we can see two examples about the temperatures calculated with the oxygen isotope for various late Pleistocene sites from northeastern Iberian Peninsula, the Abric Roumanie, the Shonras Cave, and other sites, and the comparison with other with other methods that we use to take temperatures and precipitation. Here, for example, in this square, we can see that this is the different methods, and this is the oxygen stop. The point that you can obtain with the different methods are different, but they are also a standard deviation range. But the important is that if you have a sequence and you can make an interpretation of a sequence, the tendency is the same. Also, the point of exactly the temperature were going different in using different kind of methods. Another thing that we are played last years is the improvement of different methods. This is the MER method. This is the method that I explained you about the intersection of the species. With this new improvement using this, we can calculate the potential distribution of the species to accurate the calculations of temperatures and precipitations that are different. If you have only, this is in gray, the current distribution that you can find in maps, and in black, the potential distribution also of the species, not only the current distribution. And with that, we can accurate the calculation after of mean annual temperatures or precipitations or something like this. And this is only an example of with this species, the common bowl Microtus arvalis from the, if I remember well, from the Abricrumani or the Sal side, I think. Okay, another kind of things that we are using nowadays for the identification. For example, this is for identification to help for identification of the species is the morphometric morphology that we use to separate to try to see the differences of species that are similar. For example, this is an example that is published in 2021 of mole balls that are elobius from a site in Iran with landmarks that they take semi-landmarks and the principal components to separate the different species, basically in relation with the anterior part of the teeth. This is the anterior part, posterior part of the teeth, and mainly is based on the differences in morphology in upper part of the teeth, in the anterior part. Okay. After also with small mammals, we can take DNA analysis. This is an example that we published in 2020 with the also with the common ball, with the phylogeny of after the last glacial maximum to the Holocene of this ball. This is, for example, these are colors are Italian, Europe, Central Europe, Western Southern, Western Northern, and Balkans. And this important thing is, for example, the DNA is useful to see from where the species come from. For example, this example here is the Microtus arvalis ball from the Iberian Peninsula after the last glacial maximum and the Holocene we can find here. And probably the Western populations in France come from Spain. From Iberian Peninsula in this case, and this is important things to know, to extrapolate also the known species and the different distributions in past of the different kinds of species, studying and comparing current DNA of these species with ancient DNA, because we have representation of these species nowadays in Europe. That's all. I don't know if I forget something. Thank you for your attention.